Well, good evening. Welcome to Space Oddities. Thank you for joining us on this lovely Tuesday evening in Spain. We hope you're all well. Thank you for being here, as always. And so tonight on Space Oddities, we're going to try and tackle some of the biggest questions that science is unable to answer yet. So we're going to be looking at some of the really, really big things. Also, what we would like you to do, if you have any of those big questions, things that you've always wanted to know, then pop them in the chat. And although we can offer you no guarantees, we will do our very best to answer them. So I'm joined this evening by Roger. Hi, Roger. Hi, Michael.
Good evening.
Hi there.
Hi, Dave, who's on his phone because he's got problems with his laptop. But he's still managing to zoom in from the United States, which is fantastic. And we've got somebody else from the US here, Lou. How are you, Lou?
Greetings, everyone. I'm doing well. Had a nice star party the other night.
Oh, great. Where was that?
My house.
Oh,
Invited
right.
some of my students and some of the neighbors.
Oh, good. Glad it went well.
Yeah.
And you had a clear sky, presumably.
Remarkably, I seemed to just wedged it right in between rain on both sides. Yeah.
Oh, wonderful. Daz won't be joining us tonight. He's done his knee in, so he sends his apologies. But the presentation that he had prepared, we will be having a look at nonetheless. So there we are. Just before we start, no news tonight, I'm afraid. That hasn't been much in the news, but there have been two interesting things relating to rockets this week. So the first thing that happened was SpaceX did a static fire test of their B-19 booster in preparation for the next test flight of the Starship, which is now scheduled for May the 8th. And they fired up the brand new version of the B-19 booster, the Block 3, which is about 22% more powerful, about 4 feet taller, and has a lot of new technology in compared to the old Block 2 boosters. This should make the booster more reliable and more resilient. But anyway, let's have a look and see what they got up to. So this was the static fire of the B-19 booster, and they fire the engines for about a minute, which was really good, and it all appeared to have gone very, very well indeed. They had already static fired the actual spaceship, the Starship itself, the day before, and that equally appeared to have gone well. New Glenn, the Blue Origin rocket, launched for the second time today on a mission. Yesterday, and it was due to put a $22 million satellite, communication satellite, into orbit. And unfortunately, although the launch went well, they lost the satellite because the second stage of the rocket failed to fire properly to put it into the correct orbit, so the satellite was lost and burned up in the atmosphere. Also, though, this was a first for Blue Origin because they managed to land it for the first time, or like SpaceX do, on a barge in the ocean. So well done to Blue Origin for finally managing to do that. But unfortunately,
here we go.
Might work. And it was Blue Origin's camera that froze at this point, nothing to do with us, unfortunately. So we didn't catch the actual second of landing, but it did manage to land successfully on the barge. As you
I'm hearing
second.
cheers of
So a big step forward for Blue Origin, but on the other hand, they managed to lose a $22 million satellite. So I guess swings and roundabouts is in order there. But the company who owned the satellite, who built the satellite, they were quite pragmatic about it. They said, well, it doesn't matter, we'll get the money back from our insurance company. So they didn't. It's true, yeah. They didn't do that. Well, we'll get the insurance and we'll do it again. So there you are. No harm.
What I don't understand, both companies land their rockets. That's fine. But the footprint that they land on, the little legs that go out just a little bit from the rocket with a very tall rocket, that aspect ratio just seems like a loser to me. And certainly given the difficulties we've had landing on not flat surfaces like the moon, things tilting over all the time. I think that's a bad design.
But it's worked. And
on nice, clean, level, stable, paths.
Well, I don't know, because they are landing on a barge in the middle of the ocean, which I wouldn't have said was that safe.
Right.
It is a calm sea.
Well, yes. I mean, obviously they're not going to try and land it if the sea isn't calm.
Well, the two CLIPS missions that landed on the moon that fell over were both that kind of aspect ratio, kind of not the one that worked was a little squat thing. These were tall and again, they didn't have very wide area under, with the footpads either.
No, absolutely. So there we are. But anyway, congratulations to SpaceX on the successful static fire of the brand new all singing, all dancing B-19 booster. And congratulations Blue Origin for finally landing a rocket on a barge in the ocean for reuse like SpaceX do. They're several years behind SpaceX, a few years behind SpaceX, but they got there in the end. But bad news about the satellite. Okay, let's move on. Let's go to
Andy. Can I? There's one other news item. Is it okay if I just pop it in here? And Lou probably knows about this too. Voyager 1 just turned off its low energy charged particle instrument to save power. And I mean that's how they do it. Anything that's got even solar panels, but with radioactive thermal generators, they have a priority of the instruments, and as the power goes down on the ship, they have the ones that they turn off, and LECP low energy charged particle instrument was the latest victim in Voyager 1, and they just shut that off a few days ago. Just thought I'd add that in there.
Thank you, Dave. Yes, I did see that actually. We can't hear you, Lou. You're muted for some reason.
I'm sorry. There were, as I remember, 4 and then 5 on instruments operating on each of the Voyagers. Does this take it down to 3 and 4?
I'm not sure. It takes it down by 1. I can tell you that. No, I don't know the number. I'll see if I can find it.
Thank you. Yep.
Okay. Anyway, yeah.
I mean, the thing about this is that it swings and roundabouts. They've lost another instrument, but the spacecraft is still going, and we're just praying it lasts until its 50th anniversary next year. So that would be wonderful for Voyager to be 50, and you can guarantee viewers that if Voyager reaches 50, we're going to have a big celebration here on Space Oddities about it. Probably bore you rigid with Voyager next year if it reaches its 50th anniversary, which we all hope it will.
50 years of Voyager science.
Absolutely. Unbelievable 50 years.
Google's just told me that there are 2 instruments still working on Voyager 1.
Only 2. Okay.
Okay.
Plasma.
It's just the magnetometer and the plasma wave subsystem that are active.
Yeah. I would have guessed the magnetometer. That's the least power, I think, hungry instrument.
Yeah. Just a few things in the chat here. In case you're watching, Daz, I'm not sure if you're actually watching or not, but there's a message from Ian saying, hope Daz's knee gets better. It's very kind of you, Ian. Thank you. Paul says, dark matter has one, or some scientists said they're considering whether it would be gravity from a parallel universe. Well, I'll let Lou answer that when he talks about dark matter. Ian says, what happens beyond the event horizon is one. That, Ian, is a very good question, because we can probably never know, because we can never observe anything inside a black hole. We might never know that one. Multiverses we'll talk about. So thank you for those. Any other questions that you've got that we might be able to help you with, don't hesitate to put them in the chat. Let's move on to the first question we're going to try and answer this evening, which is a logical place to start. And the question we're going to answer will just come up on the screen in a brief moment. And that question is, what was there before the Big Bang? So let me just get to the place I need to be. There we are. So this is a very common question that people have. What was there before the Big Bang? Well, we know, or at least we think we know, that the Big Bang was the origin of the universe, although it's used in a little bit of a different sense these days by cosmologists. But anyway, we won't go into that now. What was before the beginning, basically, let's say. So this raises the question, obviously, what came before it? Was there, for example, a prior universe? Was there some sort of timeless state? Or is the question itself meaningless? Can you actually ask what there was before the Big Bang? So we're going to look at some of the leading scientific ideas that attempt to answer one of the most profound questions. There are lots of ideas and theories about what was before, if you like, the Big Bang. So I'm not going to go through all of them this evening, but we'll go through some of the more prominent ones. So we have to ask the question, what came before the Big Bang? Now, according to our models, time itself began at the Big Bang. So if time began at the Big Bang, what does before even mean? And of course, the problem is that our theories are limited because our current physics breaks down at the very beginning. We cannot say what state, if you like, existed at the Big Bang, or if you want to put it like that, before the Big Bang. But what it really means is, if you think about this, whatever it was had an effect on our universe as we see it today. So there was an interaction with whatever preceded the Big Bang with the universe that we see today. And for that reason, it seems logical that one day we will be able to work it out. It's not as if it was something so totally alien and beyond our comprehension that we could never understand it. The fact that it produced the universe means that we should, in theory, be able to understand what that initial cause was. So let's start with the first one of these models. This is called the no boundary model. Stephen Hawking was a big proponent of this. So in this model, there's no separate space and time. At the instant of creation with a small c, of course, there was no distinction between space and time. There was this sort of timeless geometry. And what happened was that there was some sort of transition, and time itself emerged from that underlying geometry as a dimension. You know, we have 3 dimensions of space and 1 of time. So time sort of split apart from the geometry that was already there. It does not answer the question, how did that geometry get there? But it does sort of attempt to answer what happened at the Big Bang. And so at that point, you had time and space as 2 separate things, if you like, whereas before they had been united into this sort of strange geometry that we really don't know anything about. And if you want to think about this, you can think of the surface of a sphere. A sphere has no edge, no boundary. You can walk all over the sphere and you'll never find an edge. And because of this, there was no before the Big Bang, because time itself was part of this smooth, finite whole and not a separate thing that could be measured. And the key takeaway from this is that space and time didn't begin separately. They merged together from a deeper, timeless geometry, where the Big Bang marks not a beginning, but some sort of transformation. So that is the no boundary model. The next one is known as the Big Bounce. And what this says is that there's no beginning and therefore no end, that universes expand, reach a certain point, start contracting again, back to not an initial singularity, because the theory says that quantum gravity effects prevent that singularity, but at a point very close to the size, if you like, of a singularity, the universe rebounds and expands again. So we start off with space shrinking and the temperature rising, then the bounce, and then the universe expanding again. And the whole point about this is that it doesn't involve a beginning, that the universe may have been bouncing, if you like, forever. It may never have had a beginning. This one doesn't sit well with me because, you know, it's difficult for me anyway to conceive of something that doesn't have any sort of beginning, that's been going on forever, because to my mind there must always have been an initial cause. But it is a theory that is taken quite seriously by some cosmologists. So the idea that our universe is just one phase in an endless cycle is another idea. Then we get on to the idea, excuse me, that Ian was talking about, which was the multiverse. Now, the multiverse arises as a natural consequence from something called eternal inflation. We know that, or we think we know, that in the first squillionth of a second, somewhere around 10 to the minus 36 seconds after what you want to call the Big Bang, between 10 to the minus 36 seconds and 10 to the minus 32 seconds, there was an exponential expansion of the universe, which we call inflation. The universe may well have expanded to infinite size during that period. And if you want to work out the speed of that expansion, I think I did, and it was something in the region of 250 trillion times the speed of light, or something like that. It was many, many trillion times the speed of light. If you're asking the question, how can the universe expand faster than light? Well, objects in the universe can't travel faster than light, but the universe itself has no such limitation. It can expand as fast as it wants to. A consequence of this is that we may have this background of space, if you want to call it that, where there are new universes coming into being all the time as sort of bubbles, as shown in this illustration. And these are caused by quantum fluctuations in this in the region of space. And how many universes might there be? We don't know, possibly infinite, but it does mean that our universe could possibly be one of many. The thing to remember is that we cannot see any of the other universes from within our own universes because of the expansion of space. We can't see out into other universes. So this is the multiverse scenario, and it doesn't really have any major problems theoretically, but it depends whether eternal inflation is actually a thing. But again, it's an area of active research. Then we have what's called emergent reality. So if we ask the question, is space-time actually fundamental? Is there anything under space-time, if you like? Well, this idea postulates that there is some sort of deeper reality that space-time sort of sits on. And this is timeless. It doesn't have any boundaries. It's not differentiated in any way. And the idea is that patterns and relationships within that deeper reality, whatever it was, gave rise to space and time. And then that expands into the universe that we see today. So in this view, the Big Bang's not a beginning, but a transition where space and time take on the form we recognize. The true before, in inverted commas, may exist in a framework where time does not yet exist in any familiar sense. But it does rely on the fact that space-time is not fundamental, that there is an underlying fabric, if you want to call it that, some sort of underlying geometry to space and time, which means that space-time is not fundamental. And again, it's an area of research because it's another possible idea. So what we call reality emerges from something far deeper than the space-time that we see in our universe. So those are some of the ideas. So where do we stand at the moment in 2026, given the choice between deeper reality, emergence, structure formation, everything else that we see having happened in our universe? We're not at the beginning. We are part of the universe, emerging, evolving, and connected to something deeper. Despite decades of research, we still don't know which one of these ideas is correct. Observations help narrow the possibilities, but a full answer likely requires a theory of quantum gravity, which scientists have not got, and it's remained elusive for many decades. The brightest minds, some of the brightest minds in the world, have tried to figure out quantum gravity, and so far we have lots of ideas, lots of hypotheses, a few theories, but a theory of quantum gravity is still some distance away. And without that theory of quantum gravity, how does gravity behave at the quantum level? In other words, without that, we don't stand much of a chance of answering this particular big question. But a deeper question is, well, can we ever know? Will what happened before the Big Bang always remain beyond our knowledge? Because we don't know what reality was. If there was a before the Big Bang, we don't know what reality was. Our current laws of physics, like gravity and quantum mechanics, break down entirely at the very earliest moments of the universe. Now, that doesn't mean there were no laws, but it does mean we don't know yet what they were. To truly answer this, as I said, we need quantum gravity. Until then, we may be limited not just by what we can observe, but by the very tools we use to understand the universe. The question may not be unanswerable, but it may require a completely new way of understanding reality. The universe may not be beyond our understanding, but it may demand a completely new kind of understanding. There are other theories. There's a whole class of theories about what happened before the Big Bang, but those are the most promising ones that we know about for the moment. If you have any questions about any of that, please don't hesitate to put them in the comments. So there we are. That's before the Big Bang. So any questions from anybody? No. Okay. Right. Well, we're going to move on now to answer or try and answer the next question. And this is basically what's going on with dark matter. And I see Lou has disappeared. So anybody know where Lou has gone? No. Okay. Well, what we'll do then, we will take a break while Lou's become disconnected somehow. So let me move on to the next one then. And the next question, I will just give me 1 second to get up on the screen. And the next question we're going to answer concerns something very, very mysterious. And that is to say, dark energy. So we're going to ask the question, basically, what is dark energy? Let me just get this up on the screen. And there we are. Okay, here we go. So I think that's Lou's managed to reconnect. Just give me a second, viewers, while I reconnect him. No, not there. Okay, he's not there yet. All right. So dark energy. Now you may have heard of dark energy. It's something that is not it's not uncommon to hear about dark energy these days. So we're going to ask the question, what exactly is it? And to answer this question, I'd like to go back a little bit in time to the 1990s, when astronomers were carrying out a survey of distant supernovae in the universe, particularly type 1 supernovae. Type 1 supernovae have one thing always in common. They are always of the same brightness because they emit the same amount of energy. And we know exactly how bright type 1 supernovae are. So type 1 supernovae become, if you like, what's called a standard candle. We know the amount of light that they emit, and therefore we can use them to measure distances across the universe. So if we take a candle, for example, and imagine this is a type 1 supernova, because they are known as standard candles, because they emit always the same amount of light that we can rely on. If the candle moves away, it gets dimmer. And we can measure that brightness. We know how bright the supernova actually is, and therefore we can measure its distance. In this particular survey, astronomers were measuring distances to distant type 1 supernovae. And what they actually found was that the supernovae were dimmer than they should be if the expansion rate of the universe is correct. So given the expansion rate of the universe, these supernovae were dimmer, therefore they were further away than they should have been. This means that they have moved away faster from us than the standard model predicts. Therefore, the expansion rate of the universe is faster than we thought, and the universe's expansion is actually accelerating. Now, obviously, this was met with a great deal of skepticism when this was discovered, but subsequent observations demonstrated that it is in fact true. Using type 1 supernovae as standard candle is not the only way you can measure the expansion rate of the universe, but whichever method you use, as has been done subsequently, come back to the fact that the universe's expansion is accelerating. So this needed a name, so astronomers, in a brilliant bit of creativity, called it dark energy, the energy that is pushing the universe farther apart faster. So dark energy, the dark really means something unknown. We don't know what this energy is in the universe that's accelerating its expansion. And if we look at the history of the universe, we go on the left from what I talked about earlier, inflation, to the first particles at 1 microsecond, the first nuclei at 3 minutes, the first light to cross the universe at 380,000 years, the first stars 200 million years after the Big Bang, and the first galaxies, and dark matter creating those galaxies, or at least providing the scaffolding, if you like, on which the galaxies developed 400 million years after the Big Bang. And then 10 billion years after the Big Bang, we get to dark energy, because it was at this point that dark energy started accelerating the expansion of the universe. And then we got to 13.8 billion years as we are today. Now, the obvious question is there, what happened 10 billion years ago for dark energy to start becoming dominant in the universe, which it did? It's not the right question to ask. It's not as if 10 billion years after the Big Bang, dark energy suddenly sprang into existence and it hadn't been there before. It's believed that dark energy had always been an intrinsic part of the universe since the beginning. So what happened 10 billion years after the Big Bang? Because up until that point, the universe's expansion had been slowing down, which until dark energy was discovered seemed a reasonable thing to believe, that you have an expansion, but gravity arrests that expansion and slows it down. But then 10 billion years after the Big Bang, dark energy became dominant and started speeding the expansion of the universe up again. And what happened is this, that in the expanding universe, matter diluted. If you think of galaxies and stars getting further apart, the matter was diluted. The radiation in the universe was also diluting and moving towards the red end of the spectrum, redshifted in other words, so going to lower energy. And this combination of the diluting matter and the lowering energy of the universe allowed dark energy to become dominant. It could only become dominant once the universe had expanded and diluted sufficiently, because the thing about dark energy is its strength is always constant. It's believed to be constant. So you had this constant force, if you like, battling against gravity. And once the universe had diluted sufficiently, that matter had moved further and further apart, dark energy could become dominant, although its density does not change over time. Now, this idea is logical, that astrophysicists and cosmologists are not proposing that dark energy suddenly appeared 10 billion years after the Big Bang. It had always been there, but couldn't establish its dominance, couldn't start to accelerate that expansion until the universe had sufficiently diluted and cooled for its influence to become dominant over the others and dominant over gravity. So there's just a summary of this. Dark energy has been present in the universe since the beginning. As matter and radiation diluted in density, dark energy, which remained a constant density, started to have a dominant effect on the universe expansion. Its influence became stronger relative to matter and energy, and it overcame the arresting effect of gravity, which until then had been slowing down the expansion rate of the universe. So that's just a brief history of what we think dark energy has been up to. So let's now answer the question, or try to answer the question. So what is it? What is this dark energy? Now, we have the standard model known as lambda CDM, and we're going to talk about something called the cosmological constant. Now, in the standard model, dark energy is a constant energy of empty space itself. So empty space is not really empty. It has an energy level, which includes dark energy. That energy density says this constant per unit volume. So if you take a square parsec of a cubic parsec of space, the energy level, the energy density will be the same as any other cubic parsec of space, regardless of where it is in the universe. So per unit volume, the energy density remains the same. But as space expands, what this means is that the total dark energy actually increases. And although the density stays the same, the amount of dark energy increases. And the universe accelerates. The expansion of the universe accelerates. This is actually described very well by something that Einstein came up with, the cosmological constant, known as lambda. And the cosmological constant was something that Einstein invented in an effort to stop the universe expanding. Well, not literally, I mean, not even Einstein could do that. But Einstein didn't like the idea of the expanding universe. So he introduced a mathematical trick, which is known as his cosmological constant, to create a model that would mean the universe was not expanding because he disagreed with it. And he later called that the biggest mistake of his professional life, because as we know, the universe is expanding. But dark energy behaved very much like the mathematical trick that Einstein invented to stop the idea of an expanding universe. Now, the status of this is that overall, this is the best fitting model. It doesn't actually get to the fundamentals of what dark energy actually is. It doesn't actually tell us, the type of energy it is or where that energy came from or anything like that. But it is the best fitting model for what we actually see going on in the universe. But it does have a problem, because if you use the cosmological constant, the amount of dark energy that you get as an output that tells you what the energy density is too little by a factor of 10 to the power of 120. So there's something not quite right there, obviously, and nobody's been able to figure out yet where that is. And 10 to the power of 120, that's 10 with 120 zeros after it, too little energy, if you believe the cosmological constant. To me, that's a huge whoops moment. But it is, funnily enough, even bearing that in mind, it's still the most popular theory or the best fitting model overall, which is quite amazing, really. But another problem with it is that it does require some very fine tuning to get the actual energy density of dark energy. And when you're off by 10 to the power of 120, you're not getting there, really, are you? So that's a bit of a problem. Now, the next model is known as quintessence or dynamic dark energy. So this is what this model says, and don't forget, these are all models. We don't know definitively what the answer is, but this model says dark energy is a field that evolves over time like some sort of cosmic fluid. So its energy level doesn't remain the same per unit volume. It actually evolves. So the density can increase or decrease slowly. Why does this matter? Well, DESI, the Dark Energy Survey Instrument, the telescope that has been studying dark energy, recently released their first results after 5 years of observations, I think. And DESI seems to tell us that, in fact, dark energy is not remaining constant. It's actually weakening with time. Now, this needs to be followed up, and they've got another few years of observations before they'll be able to definitively say what's happening. But the first indications from DESI are that dark energy is actually weakening over time, which means presumably that the accelerating rate of the universe should be slowing over time. So this is interesting that this is what quintessence says. It does avoid the need for extreme fine tuning of lambda that the standard model gives us, but it does have some problems. It is being actively investigated. There's no actual evidence for it, but if it is confirmed that dark energy is weakening over time, this could be the model that is correct, that in fact it is like some sort of cosmic fluid that is changing and evolving over time. So that's quintessence or dynamic dark energy. The next one is phantom energy. This is actually stronger than the cosmological constant. In this idea, dark energy grows stronger over time. The energy density increases as the universe expands instead of staying constant. And if that energy level keeps increasing, what this could mean is that eventually the accelerating effects of dark energy will just keep going up and up and up, and it will start to actually rip things in the universe apart, galaxies, stars, atoms. And this is known as the Big Rip. So if dark energy continues to get stronger, then it can start actually affecting physical things in the universe. Now, is this a likely scenario? Well, it is allowed mathematically in some sets of data, but it does have problems. For example, with phantom energy, there are instabilities in dark energy, which means that we would never get to the big rip. But these instabilities should be evident to us if we look back in the history of the universe. And so far, no evidence for this has been found. So it's an idea, but it does have a few problems. Then we come to perhaps the simplest answer, that we've got the whole thing wrong, that there actually is no dark energy at all. All we need to do is to tweak gravity. So if we look at the model for gravity, and the idea behind this, which you might know if you know anything about MOND, which we've talked about quite a bit before, modified Newtonian dynamics, gravity behaves differently on large scales to what it does on small scales. There's no direct evidence of this, not yet. And this says, look, relativity may be incomplete cosmologically because gravity may behave differently across large distances. And therefore, the acceleration we view and attribute to dark energy may be a gravitational effect, not a new energy. It's to do with modified gravity. So the only problem with this is it requires extra dimensions, like the brain world model. If you know anything about brains, we won't go into those here, but you can look that up easily enough. It does require extra dimensions. Our 3 dimensions plus 1 of time, not sufficient for this idea to work with dark energy. We would need extra dimensions, and we have no evidence that they exist. It is being tested with surveys like DESI, with the Euclid telescope as well, but it makes some pretty precise predictions about what the data should look like, and nobody knows how it would meet those predictions. So people are a bit skeptical about this, and the fact that it requires extra dimensions means it's complicating the idea of dark energy, perhaps more than simplifying it. So, it is being researched, like all of them are, but it doesn't appear on the face of it to be the correct model, but who knows. And then we come to an idea called early dark energy, or EDE. Now, in this model, there was a temporary burst of dark energy in the early universe. In other words, dark energy started and then stopped. And the good thing about this is it helps us address the Hubble tension, because if the universe was expanding at a different rate in the early history of the universe and then slowed down again, if you like, that could help us explain the Hubble tension, the discrepancy in the expansion rate of the universe that we see between, for example, the cosmic microwave background and distant supernovae. It could help explain that. So that's quite hopeful. And yeah, dark energy decayed away before the present day. It was a brief burst. Now, this is a very active research area. Lots of efforts going into looking at this, because it does seem very promising, especially if it helps us with the Hubble tension. Still debated, not yet confirmed. Well, none of these are confirmed, really. So this could end up being the most promising explanation for dark energy, that rather than being constant throughout the universe, it came in a temporary burst and then decayed again. So so that's really interesting. Now, where do we stand in 2026 trying to answer these questions, and how are we going to get the answers? Well, the most likely one is lambda CDM with the cosmological constant, even though the energy level it predicts is out by a factor of 10 to the power of 120, it's still seen as the most likely. Perhaps, somebody's dropped a few decimal points somewhere, who knows? I'm no mathematician. But it's increasingly under pressure from DESI results showing that it looks like dark energy is weakening, supernova observations, and what are called BAO tensions. BAO stands for baryonic acoustic oscillations in the universe. Think of sound waves in the early universe. It's roughly like that. We can use that as a standard candle as well. We've got the Hubble tension again, this discrepancy that the universe seems to have a different rate of expansion depending how you measure it. So those are the things that are being looked at today. The key takeaways is we know dark energy exists because of cosmic acceleration. We don't know what it is. It could be a property of space itself. It could be a dynamic field, or it could be a sign that gravity needs rewriting. And the simple answer is, to quote the immortal Patrick Moore, we simply do not know. And there we are. Now, how are we going to resolve this? What have we got coming up that will help us resolve this question? Well, we've got DESI, as I said, the dark energy spectroscopic instrument that's doing its observations at the moment. The Rubin Observatory in Chile, when it starts its legacy survey of space and time, as it's called, and discovers billions of new galaxies as expected, this will really help us get some fine measurements on things. Euclid, which was the Space Telescope launched in 2023, which is mapping structure and geometry, and it's testing these ideas of dark energy. And the Roman Space Telescope, which is due to be launched later this year, which is specifically going to measure the growth of cosmic structures. All of these instruments and more to come will hopefully give us the final handle on dark energy for us to understand exactly what it is. So, and I see Lou's back. Welcome back, Lou. We're getting a bit worried about you there.
Thank you. I'm here at the university, and sometimes their internet access kind of goes up and down, but I think we're okay. I think we're okay for now.
Okay, great. Well, why don't we go over to you now before it disappears again?
Okay.
So Lou's going to talk to us about dark matter, which is a hot topic, if you like, in astronomy and cosmology. So Lou, we'll go over to you, if we may.
I'm going to load it up there.
I don't see it.
Oh, because I went out and went back on.
Oh, yes, of course. You went out and back in again. So you can load it up again.
Here, we'll put it back up. We'll just...
Let me just have a look at the chat while you're doing that. Let's welcome everybody. Hi, Kenneth. Hi, Deep Burrito. Nice to see you again.
Sure.
And who else have we got here? Gerard's here. Paul's here. And Jerry's here. Nice to see you, Jerry. Hope you're well. And that's all the people that have commented so far. So Ian says, as I understand it, the standard model read the standard candles is being questioned. The type 1 supernovas might not actually be the same luminosity. Yeah, you're absolutely right. There was this thing, was it a couple of months ago, that said that the age of the star that goes supernova in a type 1 supernova may affect the brightness of the supernova. And they're suggesting that different stars of different age that go type 1 supernova may have different light outputs. So we may be being misled by assuming that all type 1 supernovae have the same intrinsic brightness.
So potentially, if type 1a supernovas are not the same luminosity all the time, this could resolve the Hubble tension between the distance ladder that they provide and the CMB. We don't know.
Right. Yeah, absolutely. So that could be very interesting. But again, as with everything in astronomy, is yet to be confirmed. So follow-up observations are being done, I believe. So yeah, thanks for that, Ian. You're absolutely right. That could really upset the apple cart, as it were. Well, not upset it, but it could really help us resolve the Hubble tension, which I think is the #1 question in cosmology at the moment. So there you are. Let me just reply to Mike, who says he's got no sound. Let me just send him a message because obviously he can't hear me. Okay. I trust all you other viewers have got sound. Yes. If anybody else is having sound problems, please put it in the chat. Hi, Melinda. Fred, nice to see you. Thanks for being here as always. Okay. So we're going to move on now to Lou, and as we said, Lou's going to be tackling the subject of dark energy, which I still can't, dark matter, which I still can't see, Lou.
You don't see my presentation?
No, I don't.
Well, good Lord. Okay, let's try this one more time.
Okay.
I will actually upload it.
Yeah. I haven't had a notification. Right, thanks guys. You're obviously hearing us. So Mike's going to go out and come back in again. Right.
Well, so Andy, while we're waiting then for Lou, can I ask how do they know that the dark energy kind of took over at 10 billion years? Where did that number come from, or how did they measure that?
I don't know, Dave.
Okay. Okay. Sorry, I should have asked them.
It's not something I've actually thought about. They just say it did, and that's good enough for me because they're clever.
Of course.
So, yeah, I'm not going to argue with that.
I think this
what
is
kind of scientist should you be?
dependent.
Sorry?
I think this is kind of model dependent. If you assume, so you begin with an assumption that the amount of baryonic and dark matter in the universe is a constant. And then you know the rate of expansion, then you can dilute the bulk density of the universe. And then you can make some predictions about when that point in time would be where the density of matter is weak enough that dark energy becomes dominant. I think it's model dependent. I was kind of wondering, it was almost like a chicken or the egg thing. And that, I guess that's the question I really had is, did they get the 10 billion years by saying, right, okay, we know what the expansion is right now, so we have an idea what the dark energy is, so therefore this is the point where the matter, or did they have some observational evidence that, well, 10 billion years ago, looking at galaxies that are 10 billion years, I mean, I don't even know how you do this. Is there some observational evidence that said, yeah, but now, they started, I don't know. I guess that's my, I don't know what kind of observational evidence you'd have that you could pinpoint something, but okay. Anyway, just curious. Don't know is that astronomer, there's a little room that astronomers go to, and they just bring their dice with them, and it all looks very exciting and official, but it's
right.
Hey.
Do you see it now?
Yes, I do.
No, you weren't supposed to tell about that, though.
Yeah, but it's a good question, Dave. I'm going to look into that because that's quite intriguing. So I will report back on that. Okay.
Thanks.
So dark matter then, Lou.
All right. Well, I just love being an astronomer. I can talk all day about things I don't know about, and no one can challenge me. It's great. It reminds me of my father. My father's one of his favorite jokes was "mind over matter." I don't mind because you don't matter. So that's what we're going to talk about today. So dark matter is kind of the other end of this spectrum. Dark energy is kind of this anti-gravity force, this expulsion force, and dark matter is an attractive force. And I started thinking about this, and as I was talking to Andy, I said, oh my God, this is a 4-hour graduate level discussion, but Andy convinced me otherwise. So these are some of the areas. These are some of the areas that we're going to talk about today, like galaxy clusters, rotation curves for individual galaxies, the cosmic microwave background, and the lambda cold dark matter model. I'll say a little bit more about that. Gravitational lensing, the failed, let me just emphasize this, the failed detection of any dark matter particles, and perhaps some alternative theories. But so we have this thing that we call dark matter. We don't know what it is, so we give it a name so we can sleep at night. And it appears to comprise over 85% of all matter and a quarter of the of all the energy content in the universe. It's believed that dark matter is an unseen force that was, in fact, the architect for the universe that we see today. Yet it has never been directly observed, as much of Andy's prognostications also fall in under that category. So this is kind of the story of how it was discovered, why most astronomers believe it exists, and how we are hunting for this elusive quantity. Let's go back to 1933 and Fritz Zwicky. This is a picture of the Coma cluster, Abell 1656. It's a massive, dense, gravitationally bound cluster containing over 1,000 identified galaxies. And it's located about 320 million light years away in the constellation of Coma Berenices. It's one of the richest known galaxy clusters we know about, dominated by two supergiant elliptical galaxies, and it's crucial for studying the galaxy evolution and dark matter. Enter Fritz Zwicky. In 1933, this famous Swiss astronomer was observing galaxies in the Coma cluster, and Zwicky calculated the cluster's mass based on its observable structure. But through his calculations, he discovered that the cluster appeared to be missing some mass. If those galaxies really did contain as much mass, in other words, the stars, the gas, the dust, everything he could account for, as Zwicky observed, then they should not have enough gravitational force to prevent them from being flung out into space. In other words, there wasn't enough matter that he could account for that would keep them all rotating and gravitationally bound. By observing these galaxies within the cluster, he worked out that they were behaving as though they contained, now get this, 400 times more mass than they appeared to. And he did this by observing how fast the galaxies in the cluster were moving, how fast they were orbiting this center of mass, or barycenter, we call it. So from these observations, Zwicky coined the term Dunkel Materie, which I guess is Swiss for dark matter, to describe this unseen dominant component of the cluster. His findings were the first quantitative evidence that the visible stars and gas in galaxy clusters represent only a tiny fraction of the total mass. At the time, the community, this astronomical community, it largely dismissed this as anomalous results or measurement error. It would be nearly 4 decades before a second independent line of evidence would force the scientific world to take this seriously. So let's have a look at that. What could that be about? According to Newtonian mechanics, stars far from a galaxy center, where most of the visible mass is concentrated, should orbit progressively slower, just as the outer planets of our solar system orbit the sun more slowly than Mercury. This is because they're further away from the sun's mass, and therefore they experience a weaker gravitational force. But in 1970, Vera Rubin and Kent Ford meticulously measured the rotational velocities of stars of spiral galaxies. Star velocity off with distance from the galaxy center, as you see in the graphic to the left, which is how Newtonian dynamics would demand that they move. These stars, their velocities stayed stubbornly flat. Outer stars moved just as fast as inner ones, defying all expectations based on visible mass. This made no sense. The only coherent explanation was that galaxies are embedded with vast, invisible, dark, what we're now calling dark matter halos. Spherical clouds of unseen mass extending far beyond the luminous disk, providing the gravitational pull needed to sustain those high orbital velocities of these outer stars. While Fritz Zwicky had suggested the presence of unseen matter decades earlier, Rubin's work provided the most convincing observational evidence for its existence. By 1985, Rubin's work had gained worldwide recognition. She presented her findings at the International Astronomical Union conference, where she argued for the reality of dark matter on a global stage. This is a quote from Vera Rubin. In a spiral galaxy, the ratio of dark to light matter is about a factor of 10. That's probably a good number for the ratio of our ignorance to knowledge. We're out of kindergarten, but only in about third grade. I thought that was great, because the more we learn, even in this amazing age of discovery, the more.
Sorry to interrupt, Lou. There's a question from Paul.
Yes.
What is the y-axis label on those rotation curves? Is it velocity?
It's velocity, yeah. Right. Velocity on the y-axis and distance from the center of the galaxy on the x-axis.
Thank you. Thank you for that.
Excellent question. Okay, so we're barely out of kindergarten, right? Well, here's maybe a little bit better plot of what we're talking about. The white dotted line that we see kind of on the bottom of the graph, that's what you would expect from Newtonian physics and all the visible matter, stars, gas, dust, everything that you can account for. That near the galactic center, they would be rotating fairly fast, orbiting fairly fast, and then that drops off with distance. That's what you would expect. That's not what was observed. The observed data points are here on the top part of the graph, both from visible light and from 21 centimeter hydrogen. And so this is what Vera Rubin was meaning when she said that the rotational velocity stayed relatively flat far out from the galactic center. So a little more evidence that something is going on here. Now, that's all the easy part. Okay, here's where here's where I'm pulled to give a graduate class on this, but we won't. We'll just have a little chat. The observations of galactic clusters that Zwicky made and individual galaxy rotation curves that Rubin made were convincing, yet the most powerful evidence for missing mass in the universe was yet to be known. In 1960, Bell Labs built this giant 20-foot horn antenna. It was part of an early satellite transmission system called ECHO, essentially bouncing radio signals off a huge balloon satellite called ECHO. But the launch of the Tesla satellite a few years later made the ECHO system obsolete for its intended commercial application. So in 1964, two Bell Lab physicists, Arno Penzias and Robert Wilson, seized on the opportunity to use this antenna as a radio telescope to measure radio signals from the spaces between galaxies. To do so, they had to eliminate all recognizable interference, or you might call it noise, from their receiver, removing the effect of radar and radio broadcasts and suppressing interference from the heart of the receiver itself by cooling it with liquid helium. The result of this was the discovery of the cosmic microwave background, CMB, or cosmic microwave background radiation, CMBR. And the CMBR is the most powerful evidence for the existence of dark matter. While dark matter cannot be seen directly, its gravity left a permanent imprint on the ancient afterglow of the Big Bang. By analyzing the tiny temperature fluctuations in the CMB, scientists have determined that dark matter makes up roughly 26.8% of the universe, outmassing ordinary matter by about a factor of 5 to 1. Now, this is a fairly constant temperature, and we'll talk about that temperature a little more directly in a moment, but it is not, in fact, precisely the same temperature in all directions. These temperature differences, or anisotropies, of the CMB or CMBR can be observed by satellites such as the ESA Planck satellite. This CMBR that Penzias and Wilson discovered when they have eliminated all the noise in their data, and there was still a remnant signal, is about 380,000 years old after the Big Bang. That's the point in time at which the CMB was generated. And it shows tiny temperature fluctuations that correspond to regions of slightly different densities, representing the seeds of all future structure, of stars and galaxies that we see today. What else do I want to say about this? Okay, so it's important to know that this thermal afterglow, emitted roughly 380,000 years after the universe's birth, fills the sky at a nearly uniform temperature. And that temperature, I said I would tell you, is about 2.725 degrees Kelvin. But it contains these tiny temperature fluctuations at the level of about 1 part in 100,000. And it's these fluctuations that are major clues to the structure and evolution of the universe. This is a good representation. I'm not sure this is the original graph, but it's a good representation of what Penzias and Wilson saw. They were observing at a frequency of about a little over 4,000 megahertz or 4 gigahertz. And when they reduced their data, they found this low, steady, mysterious noise that persisted in their receiver. The residual noise was 100 times more intense than they had expected, and it was evenly spread all over the sky, wherever they looked. It was present day and night. They were certain that the radiation they detected at this wavelength of 4,000 megahertz or so did not come from the Earth, did not come from the sun or the galaxy. And after thoroughly checking their equipment, removing, by the way, some pigeons that had nested in the antenna and cleaning out the accumulated pigeon droppings of the antenna, the noise remained. And both of them concluded that the noise was coming from outside the galaxy, although they were not aware at that time of any radio sources that would account for it. This excess antenna temperature that they'd measured was the predicted remnant energy left over from the Big Bang, stretched and cooled to a temperature of and as we refined it a little, 2.728 degrees Kelvin. This is a picture of the COBE satellite, the first satellite that was sent to measure the cosmic microwave background radiation. And in the upper right here, we see the black body spectrum at that temperature as measured by the FIRUS instrument on the COBE satellite, along with error bars that you can see. It's really important to note that before the discovery of the CMB, its existence and temperature were predicted to be around, well, 7 degrees Kelvin by George Gamow in 1953, and roughly 5K by Alpher and Herman in 1948. So that is very powerful when you can predict something and then observe it, as opposed to most of the time we observe something and then say, gee, I wonder what that means. That was very powerful evidence that something is going on. Let's see if I can advance this. No, that's not what I want. There we go. So that was the COBE spacecraft measuring the cosmic microwave background. It looked fairly isotropic, but subsequent measurements of the CMB provided more and more accurate observations of its temperature over the entire sky, and most importantly, its temperature differences, which were pivotal data in determining the universe's composition. observations from COBE, and then subsequently WMAP, the Wilkinson Microwave Anisotropy Probe. Try saying that 5 times fast. And to date, the most accurate measurements of the universe's composition from ESA's Planck satellite have mapped the cosmic microwave background in extraordinary detail. These results, seen here, paint a striking picture. The matter we can see, touch, and study, which is called baryonic matter. In other words, it's made of baryons, protons, neutrons, and so on, and that make up stars and planets and gas and dust and you and me and everything we know about, accounts for less than 5% of the total cosmic budget. Less than 5%. Here we see, in this picture here we see the data from the Planck satellite that measures the CMB temperature to an accuracy of about 5 microkelvins, about 5 times 10 to the minus 6 degrees Kelvin. Pretty accurate. This map is speckled with tiny variations in temperature, which represent variations in density in the early universe. The red areas are warmer regions. Blue areas are colder regions, representing areas where matter was slightly more and slightly less dense. These variations in density were the seeds of all future structure. Tiny quantum density fluctuations in the early universe provided the seeds of all future structure. So the idea here is we see the universe today. We'd like to model what happened near the Big Bang that would produce the universe that we see today. And it does a pretty good job. Pretty good job. Dark matter, unimpeded by radiation pressure, began clumping immediately after the Big Bang, as the theory goes. Gravity drew matter into the denser regions, cool blue areas here in this graphic, which eventually evolved into galaxies and large-scale cosmic structure. Over hundreds of millions of years, dark matter condensed into these gravitational wells or halos that attracted baryonic gas. Without these dark matter halos, it's believed that baryonic matter, again, the matter that we know about that makes up atoms and molecules, that baryonic matter alone would not have been sufficient and not had sufficient time to collapse and form galaxies. So these measurements confirm the standard lambda CDM model of the universe with unprecedented detail. So lambda CDM model is the current standard model, as Andy was discussing, the current standard model of the universe's formation and evolution. The lambda in this case is the cosmological constant representing dark energy, and CDM, or cold dark matter, represents dark matter. So this sets the universe's age, these temperature fluctuations, at about 13.8 billion years, and shows it consists of about 4.9% baryonic matter, 26.8% dark matter, and 68.3% dark energy. All of this is matter energy equivalent. These data also provide a Hubble constant value of 67.4, and the units are kilometers per second per megaparsec, which I should mention is not in perfect agreement with measurements of the distance and velocity of our local scale, and this is the Hubble tension that Andy referred to. And it also matches the theoretical predictions of a flat universe. So there's a lot of information that you can get, and you, in order to do that, you have to look at the power spectrum of the cosmic microwave background and the sizes of the density fluctuations. We're not going to do that today. That gets into a little too much detail, but that is how it's done. Okay, moving on. Let's look for some other evidence for dark matter. Einstein's theory of general relativity predicts that massive objects warp the fabric of space-time. It bends the path of light around them, and massive galaxy clusters then can act as natural cosmic telescopes, distorting images of background galaxies into arcs and rings that you can see here in this image. By analyzing the degree of lensing distortion around large, massive galaxy clusters, astronomers can reconstruct the total mass distribution, including the large dark matter halo, independently of any assumption about the nature of the mass itself. This is the Abell cluster, Abell 370, and it's seen here in this Hubble image. It's a massive galaxy cluster. It's about 5 billion light years away in the constellation of Cetus the Whale, and it's famously known as one of the first places where gravitational lensing was ever observed. Its immense gravity, largely dominated by unseen dark matter, acts as a natural zoom lens, so to speak, in space, warping and magnifying the light from which more distant galaxies, or giving evidence for more distant galaxies behind it. And something you could do at home if you want, get a picture of a lot of galaxies, like maybe the Hubble Deep Field, and take a wine glass and hold the bottom part of the wine glass up to the image of the galaxies and look through the bottom of the wine glass and kind of move it back and forth, and you will see arcs very similar to this. So this idea of gravitational lensing it's actually a good comparison. This is the Bullet cluster, two colliding galaxy clusters, and they provide a smoking gun for dark matter. Hot gas slowed during the collision of these galaxies. Galaxies do collide. Dark matter passing straight through. The offset between the lensing mass and the X-ray gas is extremely difficult to explain without invoking a dark matter particle. The aptly named cluster, the Bullet cluster, is a huge structure in deep space that formed from the merging of two massive galaxy clusters about 3.8 billion light years away. Here, the James Webb Space Telescope has given scientists the clearest, most detailed look yet at the chaotic aftermath of this collision, including the location of the elusive dark matter hiding within it. Here, in this image, glowing hot X-rays captured by NASA's Chandra X-ray Observatory appear in pink. The blue represents the dark matter, which was precisely mapped by researchers with Webb's detailed imaging. Normally, gas, dust, stars, and dark matter are combined into galaxies, even when they are gravitationally bound within larger groups known as galaxy clusters. But here, with the Bullet cluster, this is unusual in that the intra-cluster gas and dark matter are actually separated, offering further evidence in support of dark matter. I have to tell you, Andy, I'm crying inside here as I become a dark matter enthusiast.
Oh, I see.
Yeah.
Well, it was going to happen, Lou, sooner or later. I told you I'd convert you.
I'm not there yet, but I'm moving in that direction. So what is it? Well, I'll tell you. I don't know. That's actually a line out of Fiddler on the Roof, by the way. No one knows presently what dark matter is, but there are a few candidates. Here they are. WIMPs, weakly interacting massive particles. These are considered leading candidates with mass, believed to interact only through gravity and the weak nuclear force.
Sorry, was the slide meant to move on then?
You should see a slide that says, what is it?
Oh, that's okay. That's fine.
And I'm just talking about the various options.
Sorry, I just wanted to make sure we weren't missing anything.
Thank you. So WIMPs, while experiments continue to narrow down their properties, they have not yet been directly observed. Okay. How about machos, massive compact halo objects? They were considered good candidates for a while, but generally no longer considered candidates for dark matter, as it's been shown that they really can't constitute the bulk of galactic dark matter. So that's not it. How about axions? Hypothetical ultra-light particles, first proposed to solve the strong CP problem in particle physics, still not observed. And hypothetical. Sterile neutrinos, maybe a type of neutrino that does not interact via the weak force, unlike standard neutrinos, making them nearly invisible. Well, they're theoretical and they've never been observed. How about primordial black holes? Well, they're theoretical. Theoretical black holes formed shortly after the Big Bang, which could range in size from an atom, that size of an atom, to a supermassive black hole. Never observed. Still not observed. Neutralinos, the lightest supersymmetric particles, often suggested as a stable WIMP candidate. They're hypothetical, not observed. How about hypers? A new class of models suggesting dark matter arose from a special phase transition in the universe, not observed. So we're looking, but we don't find any observational evidence for this. Okay, now here's where I relax a little bit. Okay, so there's this dark matter. We see evidence that galaxies are spinning too fast. Clusters are spinning too fast. Gravitational lensing appears to be real. All of this, and yet, after many years of looking, we cannot find any candidate material, any candidate particles that would represent dark matter. We can't find it. So at that point, a reasonable person might ask, well, maybe it's not really there. So what if we've been looking at the problem from the wrong angle? Admittedly a minority, but a vocal minority of the scientific community argues that the anomalies attributed to dark matter instead point to a fundamental incompleteness in our theory of gravity itself. And you might remember that Andy mentioned this in his discussion on dark energy. And that no new particles are needed, weird, strange particles that you can't see. You don't need all that. Mordechai Milgram, who you see his picture in the lower right here, he's an Israeli physicist who in 1983 proposed MOND, modified Newtonian dynamics, as a groundbreaking alternative to the dark matter hypothesis. Milgram's theory addresses the missing mass problem in galaxies, where stars on the outskirts rotate much faster than traditional Newtonian physics would predict. By changing the laws of gravity, now admittedly, the laws that have worked for us every time for the last 400 years, nevertheless, by changing the laws of Newtonian gravity or inertia, rather than adding some strange invisible matter, while the mainstream astronomical community generally supports the lambda cold dark matter model, MOND remains a significant and in some cases well-supported alternative that explains galactic phenomenon better than dark matter models, specifically when analyzing the rotation curves of individual galaxies. MOND, in fact, does a better job of fitting the data for galaxy rotations. And here you see a graphic detailing that. The blue dots are the observed data. The red curve is what happens if you try to fit that with dark matter. And the green curve is what happens when you use Mordechai Milgram's MOND theory and let gravity fall off at large scales as 1 over r instead of 1 over r squared, which is what we're used to in our local universe. And you see that the the MOND fit is much more aligned with the actual observations. This is a striking success. However, MOND cannot adequately explain the dynamics of galaxy clusters. It doesn't do as good a job at modeling that as dark matter does, without invoking some form of unseen mass anyway. It also fails to reproduce the cosmic microwave background acoustic peaks. This is the power spectrum that we didn't talk about today, and large-scale structure without substantial modification. The bullet cluster, where dark matter and baryons are clearly separated, is especially difficult to reconcile with a pure modified gravity approach. So where are we? Well, we have perhaps two classifications, two categories of solutions to our observations. We have the dark matter model, which does an okay but not great job at modeling or matching galaxy rotation curves. On the other hand, MOND, Modified Newtonian Dynamics, does a great job at matching the observed data for galaxy rotation. Dark matter fits the CMB perfectly. MOND does not. Dark matter explains the bullet cluster very well. MOND doesn't really. And there are also problems with MOND in terms of being able to create an early universe, the physics of an early universe that match what we see as we look out into the cosmos, where we see galaxies and strings of galaxies and things like the Great Wall. MOND does not do a great job with that. So we're kind of left with a quandary. Dark matter appears to be a good model, but we can't find the particles, and quite frankly, they're a little weird. Modifying Newtonian physics seems to work on some scales, like galaxies, but it doesn't do as well on larger scales, even though MOND enthusiasts will tell you that there are relativistic forms of MOND that do a much better job. But still, it's a stretch. So we're left with really not knowing. We see the observational evidence. Clearly, something's going on, but we don't know what it is yet. There are, to address a question we had earlier, yeah, you can imagine interactions with another universe, perhaps a universe where baryons have much more mass than our universe, perhaps a universe that is not well formed, and that these collisions with a multiverse universe could be providing the dark matter fingerprints that we see in our universe. This is all speculation. It's interesting, but there's no observational evidence for it. So I leave the door open with my talk. And what does our audience think? Is dark matter real? What do we need to do?
Yeah. Yes. Ian had a question, actually, not directly related to that. Interesting to know what you guys think. Ian's question is, might there come a time when scientists will know all there is to know about the universe, or will there always be questions? What do you think?
I'm remembering the words of the great physicist Lord Kelvin. He was probably the Einstein of the 1800s, mid to late 1800s. And he was brilliant, and he was also an arrogant son of a bitch. And just saying it like it is. He said at one point, surely there is nothing left to learn. All that remains are finer and finer measurements. Well, obviously he was wrong. He didn't know about mass energy equivalence. He didn't know about quantum physics and a number of other things that we've discovered. So I would tend to think probably not, but that's just my thought.
Dave, what do you think?
I have to agree with Lou. And you know, every once in a while, and I've seen this. We've seen this in our lifetimes where there's been these pronouncements. Oh, we now understand everything there is to know about such and such, and you know, it's just a matter of filling in some of the details. And the next thing you know, there's a whole new paradigm has come along, and we've completely scrapped it. So I'm very skeptical that we'll ever. I mean, it always seems that there's always a deeper layer. Once you figure something out, there's going to be something else, another deeper layer. And especially, Andy, the stuff kind of that you were talking about. I mean, before the Big Bang, it's really hard to picture how we are going to really understand, at least in detail, anything about that. But
if you can even
ask, not least of which because we know that whatever there was inverted commas before the Big Bang. it's left no imprint on our universe. You know, as I was saying, obviously there was an interaction between whatever there was before and what we ended up with our universe, but there's no direct evidence of what that was. We can surmise, we can hypothesize, but I can't think of any observations that you could do. I may be wrong, but I can't think of any observations you could do that would definitively say, yes, that's what was there before the universe. So I don't know.
I could imagine, I guess I could imagine that someone could come up with a theoretical construct that would make enough sense that even without direct evidence, it's sort of like it eliminates every other explanation or the ones you talked about, and I know there's a lot more, and actually does make sense and you know, kind of pins it down to one of those. But again, you're right. It would never be. There wouldn't be a observational evidence to prove it. It would just make sense with everything we know now. And of course, the problem too is, you know, the laws of physics were different, and so how do we even start there?
That's the whole problem. However, humans are endlessly inventive and resourceful. So I'm not saying we could never know everything, but I think there will always be questions, and you know, you can trivialize that to some extent by saying, you know, will we ever know what love is, for example, and you know, will we ever understand the human brain? I mean, we don't have to look very far; it's inside our heads, and the brain's a very good example of something. Again, that, you know, no matter how deep we look, there always appears to be something underneath it. You know, I think in theory all things are knowable, given enough time and enough observations and enough theories, but I don't think in the foreseeable future that we will get answers to a lot of those questions. But who knows?
Remember that the things we've been talking about today, these big questions, are less than 100 years old.
Yes, true.
In some cases, much less, right?
Yeah, absolutely.
What's the little Kurt Vonnegut poem? Tiger got to hunt, bird got to fly, man got to sit and wonder why. Tiger got to rest, bird got to land, man got to tell himself he understand.
Yeah,
that's cool. It's a great little summation, I think, of.
Very good. Well, so thank you for your question, Ian. Ian says Ian's own reply to his own question was that questions beg answers that beg new questions. That's his take. Absolutely.
Can I tell you? I want to tell you a funny thing. If we have a minute about Vera Rubin. I worked at Carnegie Institution just down the hall from her, so we had lunch with her every day, and she was just a great person. But she told us, and this is really funny, that back when she and Kent Ford were looking at what project to work on, this was a time, and you may be aware of this, where huge egos in astronomy were clashing about all. I mean, you know, this was back, you know, the 60s, 70s. They were really starting to discover a lot of new things. And there were all these big egos clashing, and so she wanted to find a project that wouldn't get involved in all these giant questions that everyone was arguing about. And so they decided they would do this very careful measurement of the rotation of galaxies, and then they would have a nice number to show people here's a galaxy, you know, rotation. And instead of that, they found this evidence for dark matter on the galactic scale that kind of. She threw herself right in the middle of the controversy, and completely unintentionally, though. I thought it was pretty funny when she was telling us that. Anyway.
Okay, we're going to move on now. Time's getting on. As I said, Daz was unable to be with us this evening, but Daz has answered, or tried to answer, another one of the big questions, our last big question for this evening, before we get on to our regular features. And the question is very simply this. Let me put this up on the screen. How will the universe end? So this is another question that people often ask. And Daz has put this together, as he can't be with us. He's put it together in the form of a video. So it lasts about 10 minutes, I think. So good question. How will the universe end? If anybody's got any answers to that off the top of their head, please put it in the chat. But here we go.
From humanity's earliest stargazing, we wondered not only how the universe began, but how it was.
Sounds a little weak on my end.
Yeah, me too.
Yeah, can't be hearing it at all.
Okay, 1 second.
And its fate will follow the same rules shaping it now. Cosmologists don't agree on a single ending. Instead, they study several scientific theories about the ultimate fate of all matter, energy, space.
Can you not hear that? Okay.
No, very, very
It's not
quiet.
great.
It's too weak.
Yeah.
Okay. All right then.
Well,
what we'll do-
The universe expands forever. Energy.
There therefore appears to be a problem with that. We have had big problems with that video this afternoon. So what we will do, we will carry that over to next week when we finish the solving the problem. So apologies for that, viewers, but we will answer the question: how will the universe end? Because there are some pretty good ideas about that, and they are a lot of them evidence-based ideas about that as well. So there we are. So we will then move on, and I think what we'll do now is go over, as one of our regular features, we'll go over to Roger, if we may, for a look at what's in the night sky.
Ooh, right. Okay. So everything's running towards the end of April already. So what have we got for this week? Okay. Well, we're currently coming up to the first quarter by the weekend of the moon and moving on forwards. But hopefully a few people have had a good run of some clear nights lately, and with the forecast there might be some more still ahead. So looking at the night sky, we still have Jupiter being mightily appearing over the southwestern skies. We've still got Leo and Virgo, the constellations which have a great number of galaxies that we all like to have a look at. And we're starting to see some of the summer constellations coming up with Bootes, with Arcturus coming up through. And then later on through the night, we've also got Vega and Deneb coming up to make the summer triangle. So times are moving on. But before sunrise, we do have a few planets coming up before it. We've got Neptune, Saturn, Mars, and Mercury. Of which you might be able to see possibly Mercury and maybe Mars and some Saturn short before the light gets too bright to see that. And then following on behind, and obviously after sunset, we've got the mighty view of Venus visible, although we have got Uranus fairly close to it as well. So things are looking quite nicely there. So some people might say it's a planetary parade, but that can be a bit of a challenge in some cases. But we are now into the Lyrid meteor shower, which is coming up to 20 meteors an hour. And that's one of the oldest known meteor showers for over 2,700 years, thanks to the debris of Comet Thatcher. I have gone over this before, but this is now starting to become more apparent in the night sky. So clear skies could be some good opportunities to spot some streaks in the sky. So we've also got the Venus up near the Pleiades as well as a little photo opportunity. And obviously with Comet C 2025 R3 coming through to near its perihelion, unfortunately, we will be losing that quite quickly now as it's getting lower and lower into the morning skies now, about 4 to 5 o'clock in the morning. If you can just about see it, it is getting quite low, but it has developed about a 10-degree tail, so something quite interesting to see. But unfortunately for the southern hemisphere, we'll be getting the benefit of the better opportunities near perihelion for that. The sun is looking a little bit barren at the moment, sunspot wise. It's almost completely empty at the moment, although there is a little bit of activity. Some prominences on the go, but as we can see in the far right picture there, we do have a small, well, relatively small coronal hole coming towards the facing of the Earth. So we'll see how that is, but looking a bit empty at the moment, so not much to photograph there if you were interested. But now we get to some more excitement. We've got the gallery from a few of our regulars, which is good. First one being Jerry with M100, the Galaxy in Coma Berenices, with a C-Star S30.
Oh, nice.
Hey,
And
I
that's
love
a
the
2.
color.
That's lovely.
Yeah,
Wow.
and we've also got almost edge on the Galaxy down below it as well.
Yeah.
So well done.
Brilliant. Well done, Jerry.
Excellent.
Excellent.
Yeah, with an S30, no doubt. So that's
Oh, wow.
working. Yes, and we've got a few images from Anne. This was the Moon and Venus over Howth Harbour in Dublin. This was she's put some images in with her Samsung phone, and this is what she managed to get with her camera at this time on the 19th.
That's nice.
It's lovely, isn't it?
Oh, beautiful.
And as she put in the description, you can see the earth shine quite clearly on this one.
You can.
I was standing
But,
almost at that very spot a couple of weeks ago, but it was
Oh.
cloudy.
Yes. Very pretty. Well done. And then she got also the Moon and the Pleiades together, also on her smartphone. So we see,
That's
and as you
lovely.
can see, right in the center there, with Venus just down below the pole, the telegraph poles down there.
That's amazing.
So, well done.
It's still got the earth shine as well. It's amazing.
Yep. Did
Beautiful.
well there. Not bad.
Thanks, Anne.
Yep. Who needs a C-Star when you've got a Samsung? And then we've got another little picture from the harbour again of the Moon and Venus. So she was obviously feeling quite photogenic there with
lovely.
That's nice as well.
and then
That
got
really
a nice
is.
reflection there.
It's really pretty.
That's beautiful.
So
Just,
well
just,
done
just
to
a
the
word before we move on, viewers. Don't forget, we'd love to see more photographs like this. Skyscapes with something interesting in the sky. They don't have to be taken through a telescope. And smartphone is obviously doing a very good job of taking these photos. So, we love photos like this. So send us more.
Yes, absolutely. And here's a sequence of 3 nights of the moon, which starts off from a day after new moon. So we got 1 day old, 2 day old, and 3 day old pictures of the moon.
Wow, Roger.
Beautiful.
Lovely.
That's really nice.
I think it's about the thinnest I've caught it just after a day old. So it's about a 2.7% moon. So it's been quite good, but it was quite easily seen in the sky. So it was.
What's the earliest you've caught it, Roger?
About that, I think. Yeah, that is probably about the earliest. Yeah. So it's not quite 1 day old.
Yeah.
On there.
Yeah.
And then I did a closer view from home of the central region there.
Oh wow!
I love that.
That's beautiful. Well done.
So, I thought as it was quite clear, it was a good opportunity to get some more closer detailed shots. And that's what we have for the gallery and what's in the night sky.
That would be lovely as a big print on a wall, wouldn't it? It'd be lovely.
Oh, yeah.
Could be.
Well done. Okay, so thank you to everybody who's sent images into the gallery. And don't forget, if you would like to send your images to the gallery, then attach them to an email, 1 image per email, please, and address the email to gallery@spaceoddities.space. And you, as well as seeing them here on a Tuesday, you have your own little gallery on the Space Oddities website, which is spaceoddities.space, and there you are. And just a few housekeeping bits. If you would like to support Space Oddities, you can do so in a frankly bewildering number of ways, so there's absolutely no excuse. You can, first of all, buy us a coffee, because astronomers' lives matter, and we need to keep our caffeine levels maintained. So if you could help us with that, that'd be great. You can scan the QR code here, or you can click the link that's just appeared in the chat, and that will take you to the Buy Us a Coffee page. Also, don't forget, summer's here. Well, it is here anyway. So you'll be wanting, of course, your Space Oddities t-shirts. And they are £20, including UK postage and packing. And again, scan the QR code or click the link in the chat if you would like to buy a Space Oddities t-shirt and impress the world. And also, because spring nights can still be a little chilly, obviously you may want your Space Oddities hoodie to wear out in the evenings. And these are two designs, zip up down the front or over the head models, and they are £40, including UK postage and packing. If you're buying from outside the UK, please add total £10 to the total value of your order to cover the postage and packing. And there you are. You can also, of course, make a direct contribution to Space Oddities by clicking the Super Chat icon. That's the one with the $sign beneath the chat window. And that will allow you to make a donation to us directly. All the money that we receive goes towards keeping the channel going. And your support, if you want to see us delivering the good science that we believe we bring you week after week, if you would like to see us continue with that, then your support will be much appreciated, as always. And at this point in the evening, it's time for a word from our sponsor. This video is sponsored by Picastro. It's like Instagram for space nerds. Thank you to Tom McCrory for sponsoring Space Oddities. Congratulations are in order to Tom this week. He's just become a regular writer for Astronomy Now magazine in the UK.
Oh, wow.
So many congratulations to Tom. Excellent work. I presume he'll be writing about astrophotography because he is an expert, obviously. So many congratulations, Tom, and we wish you all the best with that. Okay, what we're going to do now is to move to Dave. And Dave's going to do another look back in history for this week in bygone years, as it were. So, Dave, I'm going to hand it over to me. You just need to tell me when you want to change the slide, okay?
Okay, yep, thanks.
So let's have a look at this week in space.
Okay, so, yeah, this was, well, it's an interesting week. So, yeah, pop up the next slide. It was what?
Second. Sorry about that.
That's really recent space history.
That's right. Okay. So
no problem. So okay, April 19th, 1971. Very good and then horrible news for the Soviet Union. They did launch the very first space station, Salyut 1, which means Salute 1, or as they called it, the Durable Orbital Station 1. Just 55 years ago, but this was the first space station. But unfortunately, the first, well, okay, so the way it was, they launched the space station, empty, basically, no people on it, no crew. They launched the crew a couple days, 2 days later. They launched a crew of 3, got up to the space station. Spent a lot of time trying to get it to dock. They finally sort of got it connected, but they couldn't get the hatch to open. And they finally had to give up. And they came back down to Earth. And it's sort of a failure, but they did launch another one on June 6th. and they launched the 3 cosmonauts, Georgy Dobrovolsky, Vladislav Volkov, and Viktor Patsayev were launched there. They spent 3 hours trying to get it docked, and they did finally get it docked and get the hatch open. And so they actually ended up spending a little over 3 weeks in the space station, which at the time was a record.
Wow! Yeah,
length for being in space, because this is 1971. But on the way home, when they re-entered the atmosphere, it jogged a valve open on the re-entering Soyuz, and it depressurized, and they died. And it was a horrible thing, because I did read about what happened was, they didn't know when, I mean, of course it lands on the land. They would land these things out in the steppes of Russia. And the spacecraft came down as it was supposed to, and landed, and everyone went rushing up to it and opened it up, expecting this big celebration. And the 3 men were dead. They had just asphyxiated inside the capsule, which was doubly horrible, because when the first crew had come back from Salyut, the crew that could not get in, there was some problem with the air handling system that actually got some toxic fumes into the spacecraft. And one of them went unconscious. But after that happened, they did not, because what they did when they came down, did not wear their spacesuits, obviously. They did not change the rules after that they should be required to wear spacesuits on reentry to avoid this thing from happening. And unfortunately, it killed these 3 crew members. They did, after this, require that the cosmonauts come back to re-enter with their spacesuits on, so that they would have their own independent oxygen supply to avoid this happening again. But anyways, it was very, very sad. Very sad. All right, next slide.
I remember that being on the front page of the London Evening Standard the day it happened.
Yeah, really? Okay. See, I don't remember this, but they did have a stamp in their honor, and anyway, it was it was just one of the few sort of in-flight space fatalities. But I'll have more on that in a minute, unfortunately. All right, so next slide. And we are also at the anniversary of Apollo 16. Oh no, I'm sorry. We have the Ingenuity. Oh, that's right. Switch these around. Okay. sorry. The Ingenuity, Mars Ingenuity helicopter. And so April 19th. So 5 years ago, become the first aircraft to fly on another planet. It did a little 30-second hover, went up to about 3 meters, and then landed again. And that was a very successful test flight of the helicopter. It went on to make 72 more flights, and quite distant ones too. The only main equipment it had on it was a camera, but it made all these flights and took a lot of images of the surrounding area. And it actually worked until January 2024, when it finally it crashed. It landed. The rotors, I think, hit some rocks or something, and broke, and it became inoperable. It was a real engineering challenge, and it turns out, obviously, the atmosphere of Mars is about 1/100th density of the atmosphere of Earth. So obviously, helicopter blades have to spin a lot faster. And the problem is that it turns out that when blades are spinning at, when they reach the speed of sound, they begin to twist and deform and break. And it seems to be some sort of an unavoidable thing when you have a long, thin blade, that it can't withstand hitting the speed of sound. And the speed of sound on Mars is a lot lower than on Earth. It's about 250 meters per second, I think, 250 meters per second compared to about 340 meters per second on the Earth. So they didn't have as much to work with. They managed to do it by having 2 oppositely rotating blades, and you can see in the image there how it works. 2 opposite rotating blades, and keeping them small enough so that the tips of the blades did not reach the speed of sound. And they rotated at 2,600 RPM, pretty fast, but not fast enough to damage the blades. And that's how they managed to do it. And it was quite an achievement. I know they tested this thing in an evacuated chamber a lot. And anyway, it was an achievement. And that was only 5 years ago this week. All right, next slide. And this is where I was going. Okay, Apollo 16 lunar module, Orion. So it was the second to last, the penultimate journey to the moon. It almost didn't make it because they had problems getting it into the appropriate orbit. To get the orbit circularized at the moon, they were having some problems. They finally did get the thrusters to work correctly, but they almost sent them back to Earth without landing. It worked to go, and it was. Interestingly, it was 1 year and 1 day after the Salyut mission, the first space station was launched. It was the Descartes Highlands, so this was a very rough, rugged area. They had the lunar rover, and they traversed a lot of distance. They were on there for 3 days. There's sort of the famous picture of John Young leaping in the air. You have to look kind of closely to tell he's leaping in the air, but you can see by his shadow that he's really actually popping way up in the air there, not just standing on the little ridge that's actually behind him. He just popped himself up in the air and saluted, and managed to do that because of the low lunar gravity. All right, next one. April 21st, 2002, and you might remember this anyway. The Japanese Nozomi mission unfortunately had problems, dumped a lot of its fuel. Sorry about that. Dumped a lot of its fuel and had to rearrange its orbit and stay out in space 4 extra years, longer than planned, before it could get to Mars. And during that time, it was hit with this powerful solar storm. It damaged the communication system. It damaged a bunch of the systems. It actually still managed to recover a lot of the function, and they had gotten it to Mars, but at the last minute, the thrusters would not fire to slow it down to put it into Mars orbit. It was one of the things they really couldn't test beforehand, and they were trying to get them to start up, and they did not. And unfortunately, just flew by Mars and went into a heliocentric orbit. It flew within 1,000 kilometers of Mars, but just didn't operate. Obviously, didn't go into orbit and couldn't do its thing because of solar storms. And we've talked about solar storms before, and this is what happens. And there's just a thing of the Earth, which was, this was inbound to the Earth at the time. So the solar storm hit the Earth a few days before, and before it reached Nozomi. But then I guess they knew it was coming because, and you can see how the effect at the Earth. A couple days later, it reached Nozomi and damaged the spacecraft. All right, next slide.
Oh yeah, World's Fair.
Yeah. These are a couple little off the walls coming up here. So, so 1964, April 22nd. I remember this well. I grew up in New York and got to go to the World's Fair quite a bit. But it was a very big moment, a big exhibition for the U.S. space program, basically. It was really one of the themes of the World's Fair was just the future and technology, and of course this was the big thing. There's actually a model of the Ranger spacecraft there. They had this big U.S. space park. They had this Futurama. They had this moon dome, and it was a big deal. Anyway, it was and they really did bring a lot of the stuff to the public's attention in a big way there. So I thought to include that. Okay, and then also April 22nd, 1970 was the first Earth Day celebration, and I only put that in there because it's always been kind of it's always been thought that this was really one of the really things that spurred the idea of an Earth Day was some of the images from the Apollo mission, the Earthrise image from Apollo 8, and other images of the Earth. The big blue marble kind of images that the Apollo spacecraft took, because it was the first time that humans had been out that far from Earth and see the Earth as a disk like that. So I thought that was still a big day in exploration history in a way. Yeah. Okay, now Yeah. All right. Next slide. So here is actually the very first in-flight space fatality, April 23rd, 1967. And Vladimir Komarov, the parachute didn't open. They launched on April 23rd and re-entered on April 24th. It was supposed to be a very simple mission, just Soyuz 1. It was one of the earlier missions. His backup was Yuri Gagarin, just to give you an idea how early it was. And there's a picture of him sitting with Yuri Gagarin up in the top right there. But with all the other things that could go wrong in space, his parachute never deployed. It never came out. The actual drogue parachutes did deploy, and they were found 10 or 15 kilometers downrange from where the spacecraft crashed. But it hit at something like 250 kilometers an hour. Yeah, so it was honestly instantaneous. And just looking at the wreckage, it's like, I mean, it's yeah, it really. It looks unreal, but it was an awful thing. And actually, even sadly, it said that the handle that he pulls to deploy the parachute was pulled, and the parachute just did not come out for some reason. It got stuck. Anyway, next slide. So the first Earth orbit crossing asteroid, 1862 Apollo, was discovered. It led to the discovery of basically a whole class of asteroids, which are called Apollo asteroids. They're all named, as a group after these. And there's an example of some of the larger ones in the center there. But this was the first one that was seen, and it actually was lost. These are harder to find, and it was why they weren't found for a while, because they spend a lot of their time sunward of the Earth, and so they're not always so easy to see. They only spend a small part of their orbits outside where you can see them at night, basically, right? So they're hard to find. But he was the first one to discover it. He found 394 other asteroids in his career.
Wow.
Yeah, which is about at least 0.2 of a second of the Vera Rubin telescope, I think, but something like that. In any case, but the first Apollo asteroid. So it's pretty significant, because of course it really did show that the asteroids were, kind of all over the place. Not only that, but that they could be a danger to Earth. It's kind of always thought that was possible, but this was the first actual evidence that asteroids did cross the Earth's orbit and obviously could be a danger. Okay, next slide. And just lastly, and don't even have to say a lot about this, I don't think. No. But April 20th, 1990. So one of these things to make you feel older. 36 years ago, on April 25th, they deployed the Hubble Space Telescope. I bet we all remember that. That was an amazing thing. And of course, at first, it was also the problem with the lenses was quite an embarrassment to NASA. But then fixing it was quite a triumph. So, and then obviously everything after with the Hubble Space Telescope was just an incredible triumph for everyone, for science and for astronomy and everything. So, and I think that's it. So thank you.
Thank you very much for that look back. We tend to forget with the history of space exploration that, compared to the number of people that have been into space, there haven't been that many fatalities. But of course, everyone is tragic, and there we are. Okay, so what we can do now, if you just give me 1 second. I'm afraid there's no Einstein of the Week this week. I haven't found anything that I wanted to share with you in terms of Einstein of the Week, but I'm sure we'll be back next week. Since the Artemis 2 splashdown, it seems all the lunatics on social media have gone back to their basements and they've been rather quiet. So I haven't seen anything, but we will continue with space numbers of the week. Just give me 1 second, and we will have a look at this week's space numbers. If you're not familiar with space numbers of the week, I give you a number connected in some way with space, and you have to tell me what the number represents. So, space numbers of the week. Your first number this week is 12,700. Any guesses? Any guesses, viewers? What does the number 12,700 represent?
Number of exoplanets found?
Oh, very good guess, Michael. Totally wrong, but a good guess. No. Any other ideas? It's about 6,000, isn't it? The number of known exoplanets.
Okay. I knew it was a lot, but
yeah. Okay. No. Okay. So as we talked about the Vera Rubin telescope. It's shortly, although we don't know exactly when it's going to start its 10-year observing run, photographing the southern sky. And so far, it's discovered thousands of asteroids, in fact, 11,000 to be specific. But at the start of its observing run, until the end of next year, the end of 2027, the models say it should detect around 12,700 asteroids. So this is a huge number. 1 million is the next number. Could be anything, couldn't it?
1 million bicycles in South.
No. This is again about Vera Rubin's asteroid haul, the 11,000 asteroids. They were discovered from 1 million images acquired over 6 weeks. So over 6 weeks and 1 million images, they discovered 11,000 new asteroids. So this is mind-boggling. How many asteroids are actually going to be discovered during the whole of the 10 years of the survey? 380, and this, I'll give you a clue, this is another Vera Rubin number. This one is amazing. I had no idea this was the case. So
number of comets.
Oh no, sorry, Rod. No.
Data.
But you've got the right idea. It's actually the number of TNOs, trans-Neptunian objects.
Oh, wow!
That the Vera Rubin has discovered in just 2 weeks.
Okay.
Wow.
These TNOs are objects out beyond the orbit of Neptune. So if you go out far enough, it includes the Kuiper belt. But there's a difference. The Kuiper belt starts out at roughly the distance of Pluto, and trans-Newtonian objects are from the orbit of Neptune. So from the orbit of Neptune outwards, it's discovered in 2 weeks 380 new objects. 2 of those objects they reach 1,000 astronomical units. That's 1,000 times the Earth-Sun distance at their furthest point. So this is just mind-boggling. In 2 weeks, we've got 380 new TNOs added to the catalogue. What an amazing telescope this is proving to be, and it hasn't even started its observing run yet. This is all test data. Okay.
Well, the nice thing about that too is, they're talking about trying to find this planet X that might be out there, and I can imagine that just watching these 380 objects, and of course whatever else they discover over a short period of time, and pinning down the orbits for them, might help them actually, find this planet X if it exists. Interesting.
So we will keep you posted, of course, about new discoveries from the Vera Rubin telescope. Right, the next number is not Vera Rubin related. 44 million miles.
44 million miles.
Okay, so on April the 27th, Comet 3I Atlas will make its closest approach to the Earth, and that's how far away it will be.
Okay.
44 million miles from the Earth. 44 million miles from the Earth. So we will say goodbye to it as it goes out towards the orbit of Jupiter and beyond, and then disappears forever out of the solar system. It's been quite an entertaining comet, hasn't it? So there we are. Okay, 85 out of 91. 85 out of 91. Okay, so far this year there have been 91 space launches, 85 of which have been successful.
Okay.
So that's a pretty damn good success rate, I would say.
Yeah.
And lastly tonight, 14. 14 is the number of humans who have flown to space so far this year.
Oh.
Well
So,
done.
Okay.
there you are. So that's your space numbers of the week. More next week.
Yay.
So there we are. Okay, so lastly this evening we're going over to Michael for our regular feature of tiny constellations.
Not necessarily.
Oh, not this. Whoa. Moving up, are we, Michael? You've decided to come and play with the big boys after all. So I'm going to give you, Michael, constellation of the week anyway. So, Michael.
Give me a second. A secundo. I'll share my screen. You got that?
Yep, there you go. All yours.
Okay. So I'm going up to Cassiopeia. As you can see, it's a 5-star constellation. It's still fairly small, but quite prominent. Cassiopeia is a prominent W or M-shaped constellation in the northern sky, easily found opposite the Plough or the Big Dipper if you're in North America. Across the North Star or Polaris, it's visible all year round in the northern hemisphere, and it appears highest in the autumn, specifically in the northeastern sky in late evening hours. So, I missed a slide, I think. Sorry. This is an ancient drawing of Cassiopeia herself in her chair, as depicted in Urania's mirror, named after the vain queen of Ethiopia from Greek mythology, mother of Andromeda. She boasted her beauty surpassed that of the sea nymphs, the Nereids. Her arrogance provoked Poseidon's fury, ultimately leading to her celestial placement, a cosmic lesson in humility for all who gaze upwards, and that internal punishments. Okay, so let's look at the bright stars. And it's instantly recognizing as I say, as a W or an M, depending on him. For observers above latitude 34 degrees north, it is a circumpolar constellation, never dipping below the horizon. Best viewed, as I say, from September to early November. Okay, this is the brightest stars. First, we have Shedar or Alpha Cassiopeia. Shedar is the lower part of the constellation, shown by the arrow there. It's a bright star at magnitude 2.2, a luminous yellow hypergiant radiating a warm amber light visible to the naked eye. Beta Cassiopeia, or CAF, is a delta Scuti variable star whose brightness fluctuates subtly over short periods, making it a fascinating target for variable star observers. It's a prototype BE star, a rapidly rotating giant that ejects a disk gas, producing distinctive emission lines and dramatic, unpredictable variability. And one Gamma Cassiopeia, this is the prototype BE star, as I say, rapidly rotating giants. Okay, Rogue Cassiopeia, one of the most luminous stars, is absolutely amazingly a greater one, quite a big star compared with our sun, as I will show in this next slide. As you can see, that is the edge of Cassiopeia.
That's a big star.
And the little dot in the middle is our sun, as a comparison. So, and it's over 500,000 times brighter than our sun.
Wow.
Another star is V509 Cassiopeia, and that's the largest impression of that, I believe. It's another yellow hypergiant of extraordinary mass and brightness.
Wow.
That's Rho. Sorry. And 6 Cassiopeia, a rare white hypergiant, a testament to the dramatic, unstable final phases of a massive stellar evolution, blazing brightly before an inevitable end. Okay, so echoes of cosmic events. In November 1572, Danish astronomer Tycho Brahe observed a brilliant new star in Cassiopeia, a supernova, so bright it was visible in daylight. In daylight, its meticulous records helped to overturn the ancient belief in an unchanging cosmos. Another star, Cassiopeia A, is a remnant of a later supernova. Cassiopeia A is the most powerful extrasolar radio source in the sky at frequencies above 1 gigahertz. So Cassiopeia lies in the Milky Way, and then you can see quite a few clusters in that constellation. M52, or called at 18, is one of them. And that's quite an interesting one there. Nice little cluster is the L cluster, NGC 457, and also Caroline's Rose, which in reference to William Herschel's Sister Caroline. Okay. And another object is IC10, a small irregular dwarf galaxy located approximately 2.2 million light years away, and it holds a remarkable distinction. It is the only known starburst galaxy within our local group.
Ah.
So, exoplanets. Cassiopeia is confirmed to host 14 star systems within the boundaries of Cassiopeia. One of those star systems holds actually 6 planets, the star system of HD 219134, which is actually only 21 light years away, making it one of the nearest multi-planet systems to Earth. So, the richly populated HD 219134 system offers scientists a rare opportunity with multiple planets at variable orbiting distances. Researchers can study a wide range of planetary environments around a single star. Scientists analyze atmospheric composition, surface temperatures, and orbital dynamics to assess which worlds might support liquid water, a prerequisite for life as we know it. So again, this is a bit of folklore. Cassiopeia was the vain and most beautiful wife of King Cepheus of Ethiopia, who stands next to her in the sky. They are the only husband and wife couple amongst the constellations. Long before Greek astronomers gave her a name, the 5 stars of Cassiopeia were woven into stories by peoples across the globe. The vain queen claims chained to a throne in the heavens, forever rotating, forever humbled by divine justice. It's also one of Cassiopeia is one of Ptolemy's 48 constellations from the 2nd century AD. That contains Tycho Brahe's 1572 supernova observation. And from some of his ancient catalogue to modern radio telescope, Cassiopeia has anchored human observation of the night sky for over 2 millennia. And that's what I've got. So
thank you, Michael. Most interesting. So, so yes, Cassiopeia, we all know it. Of course, it's one of the most prominent constellations in the sky. And when it's in the east there in the summer, lots of interesting objects. Of course, we get Andromeda rising after that, and Perseus, and so lovely constellation to look at in the summer.
Right.
Okay, that just about wraps things up for us tonight. We'd like to thank you all for being here, viewers, as always. Hope you've enjoyed this evening, and hope you've enjoyed our look at some of the big questions about the universe. And as I said, Daz's video appeared to have a problem, so we will investigate that, and we'll show you that next week so that you don't miss out on that. Yeah, Ian, it is a shame we have to postpone it, but we will get it fixed for next week. I'll kick Daz and get him to read the audio. But the weird thing is, it plays perfectly on my PC.
Weird, yeah.
It's fine. So I don't know what's going on there. We'll have to investigate. Anyway, apologies for that. We will be back on Space Oddities. Don't forget, on Thursdays, we publish our Space News Weekly News Bulletin, where we just give you some of the more prominent news stories of the week. And we'll be publishing that probably on Thursday evening. So join us on the channel for the weekly Space News Weekly, aptly aimed, and we hope you can enjoy us for that. If you don't watch that, then we'll be back, of course, next Tuesday at the same time, 8 p.m. UK here on the Space Oddities channel. We'd like to wish you all a fantastic week. Have a great weekend. Hope the weather stays kind for you. And from all of us at Space Oddities, including Lou, who has had to go off and teach his students, but from myself, from Roger, from Michael, and from Dave, we'd like to wish you a very good evening. Take care. Be good to each other, and we will see you back very, very soon. And thanks for all your support.